Uh, hello everybody. How you been? I know it's not been so long this time. Um, well, hopefully you guys had a good time with the last video, and we're back. Yay! We are back with, you guessed it, complex variables. Uh, last video, let me see. Last video we went through the basic operations. We went into complex number division. Um, So yeah, we left with the answer for the last question was negative 5 over 2 minus I over 2. And so yeah, let's get into it. Next, uh, the next question is, right, next problem is it combines addition and division of complex numbers. So let me put this aside so I can have this here. Let's see. 5 plus 5i divided by 3 minus 4i plus 4 plus 3i 20. All right. So, how do we do this? Well, sadly, we will have to multiply it out. I think that's how I did it last time. Uh, yeah, I do work through these problems before doing the videos, just so I don't make such a fool out of myself. But it's been so long since I did that, I think I'm gonna make a fool out of myself once again. So let's try it out, shall we? So let's see if I remember. So yeah, we can multiply over here. 4 plus 3i over 4 plus 3i. Boom. Multiply here by 3 minus 4i. 3 minus 4i. And so we're left with 4 plus 3i times, actually, dang it, 3i times 5 plus 5i plus 20 times 3 minus 4i. Right? We have 3 minus 4i times 4 plus 3i. Dang it. 4 plus 3i. I'm a little nervous. I don't remember how to do this. So here we go. 3 minus 4i is, we can work it out. I can't work it out in my mind. I am not that, I don't have that much RAM in my memory. So we got 12, fuck, 12 plus 9i minus 16i, and then we have plus 12i. Remember the sign switches when actually minus 12. The sign switches when we square I, because I square equals -1. So it's just like multiply by -1. So 12 plus 12 is 24. 24. And then minus 7i. That looks about right. All right, so this goes below. Now for this one, 4 plus 3i times 5 plus 5i, right? 4 times 5 is 20. 4 times 5 is 20. 3 times 5 is 15. And 3 times 5 is 15, but we switch the sign. What's in minus 15 is 5 plus 35i This goes here. And this just basically multiply both by 20 since the imaginary part is 0. And so we get 60 minus 80i. Okay, so we have 5 plus 35i plus 60 minus 80i. Right? Divided by 24 minus 7i. From here we can combine like terms. So 60 plus 5 is 65. And this is going to be a minus. Don't judge me. 35 minus 80. Negative 45. So 45i. And 24 minus 7i. And so we said, what did I say last time? Right. Right. Okay. So we said that 24 minus 7i times a plus bi equals 65 minus 45i. Right. This is going to be the answer to this fraction, like the result of the fraction of the division. So we can multiply. This is going to be 24a plus 24bi minus 7ai plus 7b equals 65 minus 45i. Right. Then we have 24a plus 7b equals 65. Since real numbers go with real numbers. And then negative 7ai plus 24 plus 24 bi equals negative 45i. So we can put this into an augmented matrix. So we get the matrix 24, 7, 65, negative 7, 24, and negative 45. Right? Now we use our calculator, and we do syssolve. There it is. Syssolve the 2 by 2. We get 24 plus 7 equals 65. We get negative 7 plus 24 equals negative 45. We get we get 3 minus I. That's our answer. Like A equals 3 and B equals negative 1. And if we check, yep, that's the answer. I still got it. Hell yeah. God damn, it took 10 minutes. Wow. Or like more like 8 minutes. But yeah, that's how you do that. If you want to take a screenshot or anything, do whatever. Be my guest. Alright. So now this one is interesting. We're gonna have to play with the exponents. 3i, wait for it, to the 30th power minus I to the 19th power divided by 2i minus 1. Alright, so there is a way to, like some of you might already have like started to think about it, right? Like might have already solved it by now. um, but there is a way to simplify the top part, to simplify the numerator, and that's to remember that I squared equals -1, right? And then how do I put it? It's like uh it's like a to the b power that raised to the c power equals a to the bc power, right? We're gonna use that to that looks like an e. We're gonna use that to simplify the numerator. So and we're gonna try to get it to this so that we can get a -1. So is it 19 or 18? Yeah, it's a 19. Is it 19? Yeah, it's a 19. Okay. Would have been nicer if it was an 18, but we'll find a way. We'll work around it. Um. So yeah. So what's 30 divided by 2? That's 15. So this can become 3 times I squared. We got it. To the 15th power. This I to the 19. We're gonna go step by step because I don't really remember how I did it, and I refuse to look at the book because that's cheating. Unless I get a really wrong answer. So, and you're gonna remember that A to the B times A to the C equals A to the B plus C, right? Right. And so, uh, that's how we can simplify this 19 because we can get it to I to the 18 times I, and we can get this and then to the 9th times I, right? So we can get it like I squared 15 minus I squared 9 times I divided by 2I minus 1, right? And we can, right. So this becomes -1, -1 to 15 minus -1 to the 19th I, and from there you can try to put the -1s to the x power in the calculator. However, I'm gonna waste your time further and try to do it by hand because I feel like it, and I think it's a nice challenge. Um, so yeah, so you can get -1 to the 14th times -1. Since the power is even, the -1 cancels, and we get to 1 times -1, which is -1. So this becomes a -3, right? Minus. We can do it once. Oh, hold on. It was the 9th, not the 19th. There we go. We can do it once again and say -1 to the 8th times -1. And right, this becomes 1 times -1. Like in general, if it's odd, you can in general if it's odd, it it uh it conserves the, how do you say it? Sign. It conserves the sign, right? So am I right? I can't quite see my face. The screen sharing is in the way. So minus -1 times I, which becomes a plus I divided by 2I minus 1. And now we have a more manageable, much more manageable um, fraction that we can divide out, simplify using our method, where it's like 2i minus 1 times a plus bi, negative 3 plus I. Oh, hold on. Negative 1 plus 2i, right? Yeah, negative 1 plus 2i. Got mixed. I hate it when they mix it up. It's just, it's so unnecessary. Just keep it as is. Keep it as is, man. So negative 1 plus 2i, we get negative a minus bi plus 2ai minus 2b equals negative 3 plus I. And then we get negative a. Actually, you can skip. It's like negative 1, negative 2, negative 3. Then we get 2, negative 1, 1. Right? Boom. Now we can do syssolve again. We get negative 1 minus 2 equals negative 3. And then 2 minus 1. Oh no. 1. Here we go. Equals 1. Negative 1. Negative 1 minus 2 equals negative 3. 2 minus 1 equals 1. Yep. We get 1 plus I. Am I right? Yay! I'm right! I am right. Always. Nah, that's not true. But yeah, I think that was a really cool problem. I like the way you can handle it. You can handle the exponents because due to the what is that buckle? The cyclic effect, the cyclic thing that multiply by negative one has. It's much easier to work uh, with exponents. It's much nicer as well. All right, so we're moving on from basic arithmetic with complex numbers into um, more vector stuff. This is something where you can actually treat complex numbers like vectors, as you're being asked to find the magnitude or the absolute value of a complex number, which in practice is like finding the magnitude of a vector. So I'm gonna try to visualize it a little bit. First, we're gonna have this. So z1 equals 2 plus I z2 equals 3 minus 2i. Z3 equals, this one's odd. I mean, negative 1/2 plus, where is it? Square root of 3 over 2i. Working with this thing is gonna be, it's gonna hurt. It's gonna hurt a lot, a lot. So we're asked to find the absolute value of 3z1, but oh, actually minus 4z2. And so here I can get to explain how you can think of absolute values with imaginary numbers. So as you can recall, we can visualize imaginary numbers as being in a plane where one axis is the real part, the other axis is the. I think that's how you do it. Yeah, I think that's the symbol for imaginary numbers. And so we have 2 plus I. 2 plus I is like 1, 2, and 1. Dang. There we go. If you recall, in the real number scale, I'm gonna draw over here. In the real number scale, we have 0, 1, square root 2, whatever. And here we have -1, negative square root 2, blah, blah, blah. And so the absolute number in the real scale is the distance between 0 and that number. And so it is just a magnitude, so that's why it's always positive. It just tells you the distance from 0. And so when we take the absolute value of imaginary numbers, these being more like vectors, what we're essentially doing is taking the magnitude of the vector that's represented by the vector that represents the imaginary number. Right? So we're gonna take, so this distance, we're trying to get this distance, and to do that, we're gonna apply the Pythagorean theorem and get how much it goes in the real axis and how much it goes on the imaginary axis to get this, the hypotenuse or the magnitude of the vector. So we can do the first problem so you can see it better. So 3z1 is 6 plus 3i minus 4, actually plus -4 times z2, which is -12, plus 8i. Yep. -12 plus 8i. You guys already know how to add with imaginary numbers. This becomes -6. And yeah, -6 plus 11i. We're going to take the absolute value of it. And so to take the absolute value of it, we square both. We do -6 squared plus 11 squared, and we take the square root, because it's like 6 squared plus 11 squared equals the magnitude of the thing, right? Squared. So if we take the square root, we get just the magnitude, right? Hold on. And so what we get, if we use our handy dandy calculator, the square root 6 squared plus 11 squared, we get square root 157. We get the square root of 157. You can do the math yourself. So yeah. Oh, also, we can also visualize addition and subtraction of. I don't remember if I did this last video. I'm gonna do a quick run through. Addition and subtraction of imaginary numbers. If you think of them like vectors as well. Because if we do this, and then we have, let's say, z1 plus z2, right? 2i, boom. z1 and z2 is 3 minus 2i. 1, 2, 3, 1, 2. 3 minus 2i. I think I did this last video, did I? Anyway. z2, if we add them like vectors, and we do 3 plus 2 is 5. 1, 2, 3, 4, 5. It's going to be like around here. And we do 1 minus 2 is -1, so it's going to be actually right here. You can see that it forms a parallelogram, which is just how we add and subtract with vectors, which is tip to toe, or bottom to tip to bottom, whatever. So yeah, thinking about imaginary numbers as vectors is really helpful, at least for now. I haven't read the rest of the book, but so far it helps to think of them as vectors. They probably are vectors. I mean, the set of all complex numbers has to be a vector space, right? I'm not going to prove it right now. We got some other problems to get through. Z1 cubed minus 3, C1 squared plus 4, Z1 minus 8. Okay. Actually, I am not going to do one of the problems because it uses Z3, and I do not want to work with Z3. So we're going to do C1 cubed, C1 squared. Actually, minus that minus Z1 squared plus 4Z1 minus 8. You know, right now for this chapter, we got a lot of we got a lot of questions to go through, which this will take me like a year, probably. Like to get through the whole book. But so far for this first chapter, we're just getting introduced to what complex numbers are and how to do basic operations with them. Is one of the basic operations. If you recall, Z is 2 plus I. Right? We can get it here. And so squared is 2 plus I times 2 plus I. Dang it. Plus I, which is 4 plus 4I minus 1, which is 3 plus 4I here. And that times 2 plus I is 6 plus 3I plus 8I minus 4, 2 plus 11I. Right. So we get 2 plus 11I minus 3 plus 4I plus 4 times 2 plus I minus 8. Right? We can add these two. So 2 times negative 3 is negative 6. Actually, I multiplied. I apologize. So this is negative 1. I am subtracting, not multiplying. So this is negative 1, and this is 7 plus 7 I. And we can multiply here. 8 plus 4I minus 8. We can actually do that. And then negative 1 plus 11I. That's my answer. Let's see if that's the right answer. Where is it? Actually, I am wrong. Why am I wrong? The hell? Why am I wrong, bro? The fuck, dude? Why am I wrong, dude? So let's see. This is 4 plus 2I plus 2I, right? I squared is negative 1. 3 plus 4I times 2I, that's 3 times 2 is 6, plus 3I plus 8I plus 4I squared, which is negative 4. 6 minus 4 is 2. 3 plus 8 is 11. 2 plus 11, right? 3 plus 4I. Oh, I see where I went wrong. I see what happened. You see, I'm telling you, when there's a lot of computation or a lot of steps, I tend to fuck up. I tend to mess up. Uh, 2 plus 11i minus 8. There we go. I shouldn't have erased all of it, now that I think about it. But anyway, 2 minus 3 is negative 1. And this is going to be equal to 7i plus 7i plus 8 plus 44i minus 8. Right? I think I am not getting... The answer is negative 7 plus 3i. What am I doing wrong? I'm sure at least one person is going to like, do the thing! Just don't you see? Stupid motherfucker. If you have caught it, good for you. Tell me in the comments. I'll be glad. If you have a better way of doing things, of course. Uh, I'll be glad to read it in the comments. So, input for I don't know what went wrong. 8, 44, 2 plus 11. 2 plus I. Yeah, because that's cubed. Right. Or did I read it wrong? No, I read it right. So what's happening? Minus 4. No, minus plus negative 3 minus 4. 2 plus 11. So 2 minus 3 is negative 1. 11 minus 4 is 7. As I know, 7, 8, 9, 10, 11. That's 4. That's negative 1 plus 7. So if we, it's going to be 7 plus 51. I think it 51i minus 8. It's going to be 1 plus 51i. Actually negative 1 plus 51i. I'm spending way too much time on this problem. We already know the answer, but man, I don't know what went wrong. If you know what went wrong, tell me. Tell me in the comments. I'm gonna move on. I am going to move on for now. I'll come back later. Maybe next video. So yeah. Last problem. Oh, this is kind of a little bit, I don't know, long. So maybe I'll spend the second half of this video just on this problem. 2z2 plus z1 minus 5 minus I divided by 2z1 minus z2 plus 3 minus I. Take the absolute value of it, square. Alright, so this is, math problems are often like onions, but like inside out, you know, so you gotta go from the core out to the out. That's a bad analogy. I apologize. That's a bad analogy. But yeah, we can work this little by little, just from the inside out. Like, if you recall, I don't know why I always erase everything. Z1 is 2 plus I, and Z2 is 3 minus 2I. Right? So 2 times Z2 equals 6 minus 4I plus Z1, which is 2 plus I, minus 5 minus I. Boom. And 2 times Z1 is 4 plus 2I minus Z2, which is 3 minus 2I. And then plus 3 minus I. So the value squared. All right, and from here we can see things much more clearly. Clearly! Ooh! Ooh! So 6 plus 2 minus 5, that's 8. Minus 5 is 3, so it's 3. Negative 4 plus 1 is negative 3. Minus 1 is negative 4. Bruh. Negative 4i. Right. So this is going to cancel out. So this is going to be 4. 2 and 2, 4. Minus 1 is 3. Plus 3i. 3 minus 4i divided by 4 plus 3i. And from, I mean, we can actually do the matrix thing, so a plus bi. So we have, I'm gonna try to do it like this. 4. So we have 4, 4. And we have 3. We have negative 3 is 3 minus 4. Right? We do syssolve 2 by 2. And do 4 minus 3, 3. We have 3, 4. Oh, 4. Negative 4. And 0 and negative 1. Actually, that's not all. That's not all. That's not all. So we have 0 minus I squared. 0 minus I. 0 squared plus yeah, negative 1 squared is equals 1. 1 squared is 1. It is 1. It is 1. As you can see, it didn't take. I thought it was gonna take a lot more work, but no, it just looks scary. It's not really. So this is a different kind of problem. This next one, do we have time? Yeah. Find real numbers x and y such that. Okay. Find. Ooh, my favorite time. I get to draw symbols. Ooh. X and y, real numbers. Oh! X and y such that 3 is 3x plus 2i y minus ix plus 5y equals 7 plus 5i. Right, from here. Okay. here we can separate the real part from the imaginary parts. So we get 3x plus 5y, boom, boom, and you get negative ix plus 2iy equals 7 5i. And we get the matrix 3, 5, negative 1, 2, 5, actually 7, 5. Get the matrix. Matrices, matrices, it's all matrices. They're everywhere. They are everywhere. Plus 5, 7, negative 1, plus 2, 5, boom. X is negative 1, and y equals 2. Right? X is negative 1, y equals 2. Yeah! We got the answer, and it was easy as that. It was easy as that. Right? Hmm. Alright, so what's next? Oh, here comes a proof. I am not sure if if I'm ready for this proof. I'm not sure if we even have time for that. I'm gonna try to do one proof. So prove one. Prove the complex conjugate of z1 plus z2. I'll explain what it is in a second. Equals the complex conjugate of z1 plus the complex conjugate of z2. So the complex conjugate is just like the conjugate of a polynomial. So as you know, x plus 1. The conjugate of x plus 1 is x minus 1. Is it basically whatever behaves like difference of two squares is the complex conjugate? Because if x plus 1 times x minus 1 is x squared minus 1 squared. And so that's what we're trying to do. That's what we mean by complex conjugate, something that gives us this squared and just reverse everything back to real numbers. So what we're trying to prove is that the complex conjugate is the complex conjugate of this with the complex conjugate of the other thing. And so I'm gonna get going because I don't have that much time left. I don't know if I have that much time. I'm gonna start hurrying up. So we can have we can work out a little example to know to know like what exactly we're gonna do. So a plus bi plus c plus di. Oop, my battery's dying. Hold on. There we go. Not dying anymore. You're not dying on me. Um, c plus vi is a plus c plus b plus di, b plus d. God dang it. Di. Complex conjugate of that is a plus c minus b plus di. I did it again. There we go. E plus di. Uh-huh. I'm gonna do it both ways, using. So this is a plus c plus negative b minus di. This becomes a minus bi plus c minus di, which is the complex conjugate of z1 plus the complex conjugate of z2. So we can also go from the complex conjugate of z1 and z2. So complex conjugate of we go to the complex conjugate of each. So a minus bi So a minus bi plus c minus di. Actually, I think that's the only way we can get to. Hold on. This is a plus c. Actually, I plus plus d. Boom, boom. So this becomes um, a minus bi plus c minus di, then a plus c plus, actually, no, yeah, plus negative b minus c, actually, minus di, which becomes a plus c plus, actually, minus b plus d, and if we get the complete conjugate out of that, we're gonna get a plus c plus b plus d, which is basically the same as c1 plus c2 all conjugate. So which one makes more sense? I think it's the first one. So we're gonna go with the first one. So in writing, I don't have that much experience writing good proofs. So don't come slit my throat. All right. I'm trying my best. Okay. So we got but first, like at the beginning of any proof, we gotta lay the ground. We gotta say what we are working with and declare it. Just like in programming, when you declare variables, you declare everything in the first few sentences. Usually one, like so far as I've seen, like usually one sentence or two sentences. So you can start with let z1, z2, actually, I don't know. What's one word? Let u be be in a complex number. Be complex numbers with u equals a plus b I v equals c plus di c plus di, right? Now, complex conjugate. Where we're gonna go with a plus b? Yeah, okay. U plus b equals a plus c plus b plus d complex conjugate of u plus b equals a plus c, actually minus b plus di. I keep doing it. Di, which equals a plus c plus negative b minus di, which equals a minus bi plus c minus di, which equals complex conjugate of u plus complex conjugate of v. And the proof. And that's it. That's the full proof. That's a full proof. It is a short proof. It was a short proof indeed. A lot of proofs are short because they try to define and like defend or disprove a single idea or a single theorem. a lot of other proofs are really long, I gotta say. This second one, I don't think I'm gonna be able to prove it reliably. At least on B. So prove. Gonna get a little over the hour, but that's okay. Z1, Z2 equals Z1 times Z2. Right? Get A plus BI times C plus DI. We get AC plus AD, ADI plus BCI plus, actually, minus BD, absolute value there. And so we get AC minus BD plus AD plus BC. I'm trying to get the absolute value. I'm trying to work through an example or through a problem to know what I am gonna, how I am gonna prove the problem and what I'm gonna write in the proof. And so I'm trying to go from here to here. You could also try to go from here to here, like I did in the last example, and then determine which one's more efficient, which one's easier to write, or which one makes more sense, right? So if we get the absolute value, we get AC minus BD squared plus AD plus BC squared. Square root. So we got that. Get A squared plus B squared square root times C squared plus D squared on the square root. That means we get A squared plus B squared times C squared plus D squared, all under the square root. Right? And this, I mean, according to this proof, these two are equal. Right? Now what we need to do is get from here to here, doing some polynomial expansions, which I do not know off the top of my head. I'm gonna try to work through it. Then if I don't finish it today, I'm gonna continue in the next video. I'll remember. I'll rewatch the video and like see where I left off. Yeah, it sounds like a good plan. Thank you, Gabriel. Yeah, Gabriel, no problem. This is what happens when you spend too much time alone, talking to yourself. So we got AC minus BD times AC minus BD. We got A squared C squared. Right, and we got A squared C squared right here. A squared C squared minus A, B, C, D minus A, B, C, D plus B squared, D squared, right? So it's plus A squared, D squared plus B squared, C squared plus B squared, D squared. We're gonna find these four terms in these, like in this bigger square root. Plus B squared, D squared, right? That goes for this one. No, for this one, AD plus BC times AD plus BC. We get A squared D squared. We get that, right? A squared D squared. Plus ABCD. Oh, I think this is going to be nice. Hold on. Plus ABCD. And then plus ABCD. Yeah. Plus ABCD. Right? This ta ta ta. There's B squared plus B squared C squared. Ah, I think that's actually nice. Hold on. Plus, and then we get this thing all the way. Oh, come on. All the way over here. Right? Oh, it's gonna be nice. So we got this. We got the four terms, four squared terms like a squared c squared, b squared d squared, a squared d squared, b squared c squared, and we got these other four terms, which this cancels that, this cancels that. What we get is these other four terms, and we can. Oh yeah, that's yeah. I'm gonna go that way. I'm gonna go that way. Yeah, gonna go this way. Got a few minutes to get it, so let u be, they're not vectors, sorry, be complex numbers with, well, so we can put such that to seem more fancy, u equals a plus bi, and v equals b, actually c plus di, c plus di. Now, following following standard operations, whatever the fuck that means. I'm gonna go from left to right, so u times v, uv equals what? Yeah, okay. uv equals ac minus bd. I'm gonna skip a few so we don't have that much time. AC minus BD plus AD plus BC. Oh, plus AD plus BC I. So the value of UV equals AC minus BD squared plus AD plus BC squared. And from here we can get off the rails and start doing this. So which equals AC's. I'm just gonna copy it. I'm just gonna copy it. And I put it on the square root. Boom. Boom. There we go. Put it under a big square root. Boom. I'm already past an hour. Wow. Big square root, which equals all the square terms. So a square, c squared, b squared d squared plus a squared d squared plus b squared c squared on the square root, which equals, look at this. Actually, I forgot where I was. A squared plus b squared, right? Times c squared plus d squared, square root. We can separate them. B squared times the square root times the square root of c squared plus d squared, which equals the absolute value of u times the absolute value of v. Yay! We got it. We got it. Oh my lord. We did it. That was very long. Wow. All right. So yeah. So that's it. That's it for today. Oh wow. So um okay. So what we did today, we just went we just finished 2 pages out of, I think it's 30. I think it's 30 pages or something like that. Like it gets crazy. It's crazy. Then wait. Oh yeah. Yeah, here we go. Here we go. Chapter 2. We get, I kid you not. What's 32 minus 9? We have 23 more pages to go. This is gonna take a long time. This is gonna take a really long time. But you know, little by little, we'll get it. We'll get it. I'm thinking about doing this for a long time. I want to finish these books. Yeah. Hopefully, I will have time later. But yeah, we've done a little more of basic arithmetic with complex numbers. We've worked with funky powers of I, and then we worked with the absolute values of complex numbers, and then did some proofs on the absolute values of complex numbers. And that's about it. That's all we did. 1 hour. That's all we did. Well, I hope you liked the video. If you liked it, like. If you want to see more, subscribe to see more. So yeah, see you in the next video. Bye.